Okay, all right. Good evening, everyone. Welcome. Whoever is comfortable, putting on their video so we can enjoy seeing our friends. You're certainly invited to do so, but if you prefer not, please make yourself as comfortable, however works best for you. Welcome to our first Tuesday night talk after the Yom Tovim. We had a few before in the late summer. And we have a really interesting talk tonight. Next Tuesday, which will be election day and election night, I think we're not going to have a talk, but after that, we should be having a really interesting, engaging expert speakers, teachers. The plan is really basically every Tuesday, so look out for that information. The talk tonight, before I introduce Dr. England, is sponsored by Mordechai and Sharon Kramer. Thank you to the Kramers. It is being sponsored to commemorate the yahrzeits of Mordechai's grandparents, Tirza Kramer, Tirza Bat Mordechai Vishoshana, and also Benjamin Silverman, Benjamin Laban, Shlomo Behudel. And it should be as a chusr for their neshamas. And we thank the Kramers, and we welcome, looks like there's some other members of the Kramer family. And that's another great benefit of Zoom, that we can gather from afar. So thank you very much. We're very happy to be able to have you. Our presenter tonight, our teacher, is Dr. Jeremy England, who many of us know from the community. I'll give you first his official, very impressive brief biography. Dr. England is the senior director in artificial intelligence at GlaxoSmithKline, as well as principal research scientist in the School of Physics at Georgia Tech, and is the former Thomas D. and Virginia W. Cabot Career Development Associate Professor of Physics at MIT. He was a Rhodes Scholar, a Hertz Fellow, and was named one of Forbes 30 under 30 rising stars in science. And he lives with his wife, Elena, and their children here in Brookline. The Englands are going to be moving to Israel soon, so it's also a nice way for many of us to see Jeremy and to wish him and his family well on their upcoming move. Not included in this professional bio is also that Jeremy, within the past few years, expanded his official studies and added to his collection of degrees smicha. So really is Rabbi Dr. Jeremy England, I think was it with Roy Bravender?
Yeah.
Okay. And that's sort of the segue into the talk tonight. Jeremy, of course, is a great scholar and intellect, and he's a very creative person with many innovative ideas. And he has had such innovative ideas in science, when his expertise is beyond me. And as well as within the world of Torah, Divrei Torah, he has many very creative, innovative ideas. And tonight's talk, I think, is gonna be a little bit about bringing a lot of those creative ideas from those different fields together. Jeremy recently published a book entitled Every Life is on Fire, How Thermodynamics Explains the Origins of Living Things. You can get it on Amazon or anywhere else you buy your books. And tonight's talk, I think, will be presenting to us and discussing with us some of the big ideas in that book. And the title of tonight's talk is Every Life is on Fire, The Burning Bush, and the Physics of Lifelikeness. Before I turn over to Jeremy, just a couple points. One, tonight is being recorded, so just to make sure everyone who's on is aware of that. And hopefully we'll have the opportunity also for questions, for discussions. So Jeremy, you'll sort of lead us how you think that's best to do, but people can chat to me their questions to share with Jeremy or ask to be unmuted, and either at the end or wherever Jeremy feels appropriate to ask a question or make a comment. And with that, Jeremy, please begin.
Thank you so much, Rabbi Hellman, for that warm introduction. It's my great pleasure to get a chance to address this group. As Rabbi Hellman alluded, the talk that I have planned both aims to, on the one hand, be about discussing some physics and some science, and bringing in ideas from that part of the worlds that I inhabit, and at the same time also to get to talk about Torah. And actually, both of those topics are very natural to bring in talking about the book that Rabbi Hellman mentioned that came out recently, because it's a book on the one hand that intends to teach a general audience about some of the work that I and my coworkers, first at MIT and then elsewhere as well, have done in the last several years on research in the sort of the realm of theoretical physics at the boundary between life and non-life. And I'll explain what I mean by that. But at the same time, the way that I wrote the book was kind of in a wrapping that tried to make the whole thing at the same time a Dvar Torah. So that although if you counted the number of words, I would say more of the book is about physics. Every chapter thematically, and in terms of the epilogues written for every chapter, and also the introduction and conclusion, pull together different aspects of what you might call a single Dvar Torah, about a single passage in Sefer Shemot, in the book of Exodus, which I think can be read many ways, and that we're all probably familiar with in one form or another, but where the reading that I try to give to it is connected with a search for a commentary within the Torah about its perspective on the boundary between life and non-life, and sort of a contemplation of what it means to the human condition to discover about ourselves that we're made of afar min adama, right? The dust of the earth, that in some sense, living things are composed out of material that seems to be not living to us. So then what do we do when we're confronted with that fact? And how does the Torah guide us in our reaction to that? So it'll be a bit of a roller coaster in some sense, because there'll be a few different kinds of perspectives of talking about things. And you know, the subtitle of the book, as Rabbi Hellman read it, is how thermodynamics explains the origins of living things. But you might read it with the emphasis of how thermodynamics explains the origins of living things, in the sense that the physics in the book is trying to talk about the world in one language and from one perspective. And then I couldn't help but bring in the sort of undergirding foundation of Torah while engaging in that discussion, because it feels too important to me, to that whole topic, to leave out. So we'll see if you get a little taste of what the book is like in the ground that I try to cover. I'm going to start off by just talking about physics, and then we'll transition over into kind of shifting perspectives and looking at things through the lens of this passage in the book of Exodus, when Moshe Rabbeinu is encountering HaKadosh Baruch Hu at the Sneh, at the burning bush. So the famous dialogue between Moses and God at the burning bush, where Moses is given 3 signs to bring to the Israelites in Egypt. So without further ado, why don't we just launch into looking at some slides together, and I will share my screen in just a moment. So are people seeing the slides okay? Mm-hmm. Great. So to start off with, I think we can just contemplate a little bit about what living things are like in their properties that makes them so impressive to us as hunks of matter, so to speak, that are very different than other ways of putting together the same pieces, right? So whether you're talking about the world as a physicist who sees atoms or molecules or even smaller particles, or even talking in the language of Torah, where we're told we're dust, and to dust we will return. So there is, again, the same kind of recognition that we're a particular way of putting together stuff that when you clump it together in other ways is not nearly so remarkable. The question is, what is remarkable about living things as compositions of different pieces, as assemblages of their constituent parts? And I think that when talking in the language of physics, the way that that breaks down is you want to start to identify different things that living things do that seem sort of exceptional in comparison to other pieces of the world. Living things make copies of themselves, they harvest energy from their surroundings. So in other words, they reproduce and they find food and grab onto that and ingest it, etc. They also predict the world around them and become in their motion and in their structure, well matched in certain ways to very particular patterns that they encounter in their environment. So there are a lot of things that you can break apart about life and say, each on their own barrel, how should I think about such a phenomenon from the perspective of physics? And I think we start with taking inspiration from living things themselves. So if you think about a bacterium sitting in some environment, what it means to say that that bacterium is exceptionally adapted to the environment where it lives is that when we look at the structure of the living thing, there are particular ways it's built that are very good at interacting with the environment. And what I mean by that is that, let's say there's some sugar in your environment and you're a bacterium. If you have the right enzymes, you can break down that sugar and you can use the flow of chemical energy from that breakdown to repair yourself and to grow yourself and to do all these productive things that keep you a healthy, happy bacterium. And if you don't have the enzymes, then you can't do that. And so the same environment either is a source of energy for you or isn't, depending on your shape, depending on the structure that you're in. And I think we tend not to think about living things in these terms, but as a physicist, if you think about a bacterium and you now say, what if I took the atoms the bacterium's made out of and I just kind of scrambled them? I rearranged them in space in a random way. The typical random rearrangement of the constituent parts, the result of putting a bacterium, so to speak, in a blender is not going to be as good at doing what bacteria are good at as they are. And that seems like a trivial point to make, but what it underlines is that when we recognize lifelike function, when we recognize the success of a particular form in accomplishing a particular task, that really involves an implicit comparison to random rearrangements of the same building blocks, which are not as impressive to us. And so that undergirds the idea of the form being exceptionally good at something, right? That it's compared to some naive model of how much worse we'd do if we didn't have architecture, if we didn't have some kind of special arrangement of the pieces. And I think that that's a pretty broadly applicable principle, whether you're talking about rearranging the pieces of an automobile and trying to drive it afterwards, or rearranging the pieces of a bacterium and trying to call it anything impressively lifelike afterwards. So the question is, in some sense, how do those building blocks get into exceptional shapes, right? Because we can make an argument in biological terms if we know that living things make copies of themselves and they pass their traits on to their progeny, then you can start to make an argument for why the passing on of traits that help you to reproduce could ultimately lead to the accumulation of those successful traits in the future population. And that is the grand saga of the Darwinian argument for how evolution of living things can unfold over time through natural selection. And that's an interesting story in its own right, and we're not trying to displace or supplant that. But if you think about things now in terms of atoms, it's harder to tell the same story, right? You have different atoms that living things are made of. They're made of carbon, nitrogen, oxygen, sulfur, phosphorus, and some other trace element. You could put those atoms together in all sorts of different ways. You could take the same pile of atoms that is a whale, and if you rearrange them, you can make a lot of fish or even a lot of hamburgers or whatever you want, right? Because the chemical composition is really not so different among different living things. It's the particular way that those pieces are put together that differs, and that gives them their unique and distinctive properties. And another thing that's true with evolution is that you can have the same environment and the building blocks get put together a different way each time, just because there's a certain amount of unpredictability to how things clump together. So there's commonalities between the different possible outcomes that sort of have at some broader and more qualitative level to do with what they're good at, but you could have two different ways of being good at the same thing that just result from assembling the same building blocks in different ways. And so this isn't about the exact prediction of where every atom falls into place, but it's more about the holistic property of the thing as a whole, and whether you can predict something about the holistic properties of a whole collection of pieces of matter as they evolve and change their configuration over time. So everything I've been talking about so far is talking in analogy in some sense to how this works when talking about living things. But the pertinent question to ask as a physicist now is, can I generalize this idea to talking about things that aren't alive? I just have pieces of matter that could be stuck together in different ways. Maybe they have different sort of sticky ends, and so they like to kind of clump together in particular shapes. Some shapes are more stable than others, but there's still this question of, all right, in an arbitrary situation where I have a particular set of building blocks and maybe my environment has certain sources of energy in it, which you need in order to get lifelike behaviors, and we can return to that point if people are interested, then why would I favor one shape over another? What, I can make the argument that I just made, the sort of Darwinian argument. If I have bacteria in a jar and I say the ones that grow fastest are probably going to have to eat the sugar well. And so in the future, there'll be lots of bacteria that are good at eating sugar and not so many bacteria that are bad at eating sugar. But I don't have that kind of argument that I can make when it's just kind of naive, dumb building blocks sort of jittering around and sticking together and banging into each other. So why would you get one shape instead of another shape when you think in these physical terms? I think I'm going to skip over this and circle back if someone wants to get into a little bit more detail, with equations if people are curious. Well, maybe I'll make use of the picture here. So we don't have to talk about any of the equations, but basically the idea here is that what you're conceiving of in a scenario that we're interested in is one where I have a bunch of building blocks and maybe they're sitting at some temperature. And in the language of physics, what it means to be at some non-zero temperature is that there's a certain amount of random jumping around that the molecules are doing all the time. So we don't experience temperature as randomness because we're big things and we're not, living down at the level of single molecules. But temperature at the level of molecules basically has to do with how fast everything is randomly flying in different directions. And so if I have a bunch of building blocks and they're at some temperature, that the temperatures tell me how violently they're jiggling around and randomly changing their shape. But then they also have some tendency to stick to each other and clump together. So sometimes they get knocked apart by the jiggling. Sometimes they find each other and get stuck back together. And then you have what you call a drive. So a drive is like some external source that's pushing on the system. It might be a light source that you're shining with a particular color. It might be a sound wave with a particular pitch. It might be chemical fuel that you're dumping on the system all the time. So lots of different things could play that role. But the scenario we're talking about is, given the way that I'm driving the system, the energy source that I provide, and given the way that these different building blocks kind of like to clump and stick together, how do I now make a prediction about which way of assembling these things together is going to be very likely after a certain amount of time? And the intuition you want to try to develop for this is to think about every shape that these things could take as corresponding to a location for different things that you might imagine. Maybe a ball rolling around in a landscape, like a mountain range, or maybe a guy jumping around on a pogo stick. So there are different analogies. The relevance of the guy jumping around on a pogo stick is that it gives you a little bit of a sense of why external energy sources matter. If I just have a guy in a pogo stick, let's say he has a little bit of energy that's internal to the system that is stored up in the spring, he can jump over a wall, but he can also jump back the way that he came, because when he lands, he sort of compresses the spring again, and then he can jump back the way that he came because he stored that energy, and he can go back the way over the same barrier with the same stored energy. So that's analogous basically to the situation when there's no external driving, when you don't have an energy source. Every way that you can go one way, you can go back the other way just as easily. And that's a real problem for kind of the evolutionary lifelike scenario, because evolution is all about directional change that is very progressive in one direction and doesn't really undo itself. You don't ungrow plants and you don't unevolve specialized lifelike structures. Once you get there, you kind of are stuck with it. And so in order to have that kind of behavior from a physical standpoint, you need external fuel sources. You basically need something dumping energy into the system that plays the role of food or sunlight or what have you. And that's like giving this guy a jetpack so that he can jump over the wall, and then he doesn't have any more fuel and he can't go back the way he came. And so every jump over a wall, you can think of as being like a little change in shape for this collection of particles. It's a hard analogy to fit inside one's head, because usually when we think about changing location, we think about moving around on a map or moving around at best in three-dimensional space. And if I have lots of particles, then in order to call every change in shape a change in location, it's like I'm moving around in a space that has many more than 3 dimensions. So that's the abstraction that's very difficult to wrap our minds around. But if you can kind of find your way past that analogy, then every time your collection of matter changes shape, perhaps somewhat randomly, it's like you made a little move. You jumped from one place in a mountain range to another, or you jumped over one fence and landed in a different place than you were in before. And so the point is, if you have this whole kind of maze of fences that you can explore now as you change shapes, then if the system is getting supplied with external sources of energy, then it's all about sort of when you get a little jetpack boost that allows you to make a change in shape, and then you can't undo that change because now you've sort of burned through that fuel, and the place you landed, you don't have a jetpack, or you're not absorbing energy in the same way from the environment. So this is the crux of the physical argument. To summarize, if I have a collection of particles, and if the way it absorbs energy from its environment depends on its shape, and we can talk about why that would be in a second, and if also when it absorbs energy from the environment, that helps it to change its shape in particular ways, that's kind of a feedback loop that closes, right? Because now the way that I change my shape affects the way I absorb energy, and then the way that I absorb energy affects how I change my shape again. And I start doing this exploration of the space of possible ways of changing shape that's biased by how I'm absorbing energy from the environment the whole way along. So that my relationship, the way that I'm acting as an antenna for the source of energy in the environment, actually has an impact on whether and how I'm able to change my shape. So just to give you a sense of how the simple physical version of this works, imagine a glass that I can subject to a tone. So I'm playing this tone, it's at a particular pitch, it's vibrating, the glass is resonating, and actually eventually the glass might even shatter as a result of that. We usually think about varying the pitch of the surrounding sound field, and then maybe the glass shatters because it resonates, or maybe it doesn't shatter because it didn't move around a lot. It wasn't good at moving with that pitch of sound. Because as we notice, so we play with glasses at a dinner table or something, even when we're kids, that they have different pitches. They sound different depending on what they're shaped like and whether they're full or not. We don't as often think about the same glass being reshaped and therefore changing how it moves in a fixed environment, in a fixed sound field. So if you think about the environment as the pitch of the song, and you hold that fixed, you now say, depending on how that glass is shaped, it either will absorb a lot of energy or it won't. And so its ability to act as a receiver for energy from the environment is going to affect whether it resonates and shatters on the one hand, or whether it kind of wobbles a little bit but doesn't really move much and therefore doesn't shatter. So you can have ultimately these very irreversible consequential changes in how your shape evolves over time that have to do with the shape you are in currently and whether or not it acts as a good receiver for the energy source in your environment. That's the fundamental physical idea. And now how that plays out in terms of what you can get from that as a result, you have to kind of drill down into a particular model system. So, I'll just give you an example and we'll close up the physics part. We'll talk some about shifting perspectives and talking about it through the lens of Torah. And I want to leave a lot of time for questions and discussion at the end. So if we now talk about a particular system, this is something that we studied in simulation. Basically, you can just take a very simple simulation of some masses connected by bonds, where the bonds are kind of like springs that have two settings. They can either be long or short. And whether they get popped open or pulled closed just depends on how those masses are pushing on each other. So it's just very simple Newtonian physics. It's just the same equations you learn in a freshman physics class, except for the fact that we have lots of these masses and bonds between them. So it has this kind of random assemblage of different pieces that are pulling on each other. And that's kind of trying to simulate in a primitive way the diverse combinations of things that you get from chemistry. Because the key point is that you're not going to see interesting lifelike fine-tuning behavior if your system doesn't have a whole library of different ways it can be put together that have fundamentally different properties. If I take the same pile of carbon, nitrogen, oxygen, et cetera, like I said, I could make a pile of fish or I could make a whale, but that's not always true, right? If I had only helium or something, it would be much harder to build it into different things with different properties, because helium just doesn't really want to play along with other helium atoms very much. So it does depend on what kind of material you're working with. But if you're working with a material where it sort of has a lot of different ways it can behave depending on what shape it's in, and it likes to jump between those different states and sort of has different little pockets of the space of possible shapes that it can get stuck in, then when you take a system like this and you just solve simple freshman physics equations for Newtonian mechanics, where you're just taking a piece of the system and wiggling it, where you pick some frequency. So this is like just picking the tone or the pitch at which you're singing at a glass. So you pick one frequency, it's the timing of how you're moving this one piece of the system back and forth. And because you're moving it, you're supplying energy, and it's causing all sorts of jumblings and rearrangements in the system, and things are sort of bouncing off of each other and pushing on each other. And at first it seems kind of random what happens. But then as time goes on, eventually the system stops evolving as violently and it gets stuck. It gets stuck in a particular shape that actually it has a very hard time getting out of. And this is one kind of example of a fine-tuned behavior, and you could talk about other ones. So I don't want you to hope or imagine that this is going to be a complete summary or sort of talisman for all kinds of aspects of lifelike behavior. But one kind of lifelike behavior that I think is distinctive and that a system like this is exhibiting is that living things are good at absorbing energy from the source in their environment without being rearranged or blown to smithereens by it. We don't really worry about this because we don't think much about it, but energy is what we're trying to get from our food when we eat it, physically speaking. We eat food that's at higher energy, and then, you know, the fact that it's at higher energy allows our digestive system to harvest all this chemical energy, and that kind of pushes a bunch of chemical water wheels in our body around, so to speak, and that helps us stay in the shape that we want to be in. But you couldn't say, oh, well, if I just need energy, then I think today I'll just take an equivalent dose of dynamite or gamma radiation or other sources of energy that is the same amount of energy, but in a different form. We care about the form of the energy that we absorb. We need to absorb very specialized forms of energy that are in tune with the structure of how the living thing is assembled in order for the energy to be able to flow through without breaking things. But if we put an arbitrary source of energy through, then it will definitely break things and it will jumble things up a lot, and we call that damage. So what's interesting here in this example is that this type of system, and we've studied many examples of it, and so it's quite a robust trend across any random realization of hooking particles together in all these different ways, is that these systems learn to find ways of being shaped that are very robust and good at absorbing the energy from the environment without getting randomized and rearranged by it. So that's not all of what lifelike behavior is, but it is a fine-tuned behavior, because if I change the frequency, just the frequency, like the timing of how I'm wiggling this particle in this system, then it will suddenly start randomly jumping around again and rearrange itself until it finds a new state that is well adapted to that new environment that I provided with. So it definitely has this kind of fine-tuned, evolved matching between the system state and the environment. I just want to present one other example of this because it's kind of fun. This is another case where you start wiggling an energy source. The system is kind of at first seemingly randomly exploring the space of possible combinations and finding an arrangement of how to bind all the different particles together in a particular shape. But then once it finds this state that it's settled in, what's interesting here is that on a short time scale, it looks like it's just kind of wiggling a little bit. So it's absorbing energy and it's not getting rearranged by the energy it absorbs. On a longer time scale, though, what you can see is that it also has become a motor, because it's taking the energy that it absorbs and using it to pump a piece of itself around in a circle. So in a kind of molecular motor sense, what you have here, just from a random bundle of different springs that are randomly hooked together, is you've self-organized just by wiggling a source of energy in the system, something that can take that energy source and turn it into essentially a structure that would be equivalently capable of, so to speak, pulling a bucket up out of a well by turning a pulley. So that, again, it's not everything that life does. It's one aspect of lifelike architecture. But what it points to is that with very random initial conditions that are very primitive and very simple interactions between the pieces of the system, it's actually not so difficult to get an emergent behavior that we think of when we recognize these kinds of things going on in living things as being exceptional in their architecture. So many aspects of what we see as being exceptional in the architecture of life, it may be possible to get a kind of a rough cut of that architecture from physics that's actually quite simple and quite broadly discoverable in a lot of different settings that we see in the world and nature and could also put into the laboratory. So now I want to pivot over to talking about things through the lens of Torah. I just want to check how I'm doing on time. Can I ask Rabbi Hellman what time it is after 8 o'clock? Oh, I think you're muted, maybe.
I am muted. Let me go run and check. I can't see on my computer because it's
Or maybe someone else.
Screen share. Here, hold on. I'll just.
It's 8:34.
Oh, okay, thank you. Excellent. Now the question is, what on earth does this have to do with talking about things through the lens of Torah? And the way that I started off approaching this is I already knew I was writing a book about the physics aspects. And I think I was conscious of the fact that if you just talk about the physics, you can't really pretend that people are only going to keep the discussion in that domain, because when you start to talk about the boundary between life and non-life, it immediately brings in other aspects because we're curious about those, and they have deep meaning and there are deep sensitivities in a sense that people have about how to talk about this question on a variety of scores and for many good reasons. And so I didn't want to just put a bunch of ideas out for discussion without weighing in on some of these aspects. And so I decided that I should at least go and look and see, all right, if I want to bring in those aspects, I need to find a commentary in the Torah that seems to speak to this topic. And I was very delighted and gratified to find that once I went looking in that way, that it was quite striking to me the degree to which there's a particular passage that seems to be in a language that's obviously relating more to the everyday experience of the human being, is trying to grapple with this same kind of natural philosophical contemplation of what life is as an assemblage of materials that seem not to be alive. And I don't want to say that the passage we're going to talk about is only about that by any means. It clearly, in simpler and even very sophisticated readings, is about other things. The passage where Moses is at the burning bush and being given these signs, it's about the exodus from Egypt. It's about the birth of Am Yisrael as a nation. It's about all these different things that have nothing to do with physics per se. But we say Shivim Panim La Torah. There are many different ways you can read the same piece of the Torah, and the beauty of it is that all or many of them can be true. And so if you start out just by thinking about what happens at the burning bush, you start with a plant, a living thing that is on fire, but it is not consumed by the fire, which already is a great example of the notion of a living thing that in some sense is on the brink of not being alive. Like if you're on fire, you're not supposed to be alive. You're supposed to very quickly stop being alive because fire seems to randomly rearrange its constituent parts and tear them to pieces. And so the notion of a bush or a plant or a living thing that is bo'er ba'esh, that's burning and on fire, but it is not consumed, is exactly this kind of, it's raising the question of how is it that you can have all of this motion flowing through what a living thing is, but it's not tearing it to pieces, but instead it has kind of a coherence or a matching to it that orders it rather than disordering it. So already some of what we've been talking about in the physics, I think, is evoked by this first image that we're provided with the sneh, with the burning bush. But then if you go further in that same passage, then you can find other things that seem also to be about this theme. Because then when you go to, let's skip over this, then when you go to the staff that turns into a serpent, the mateh that turns into a nachash that Moshe is holding, this is, in a sense, about a shifting of perspectives on the same piece of the world, right? The serpent is the most staff-like living thing. So it's not, and he threw his staff on the ground and it turned into an elephant. He threw his staff on the ground and it turned into a nachash. And that's not accidental, I think, because what it's calling your attention to is the possibility that what we're really talking about here is the shift in perspectives on the same thing, right? That you could look at the same piece of the world and you could see an inanimate mateh. A mateh is lifeless. It is an instrument in our hands. It does what we say. It is metrical. It is regular. It is predictable, right? And then a serpent is a living thing with its own agency, with unpredictability, and with a sort of integrity unto itself that is not sort of being directed by someone else or not being measured or used for measurement. And so the fact that these two images are combined in this moment is kind of asking you, perhaps, you know, can you look at the same thing? And if you look at it from one perspective, you'll see a bunch of matot, so to speak. You'll see a bunch of staves. And this is how physicists look at the world. They see inanimate, tiny particles that each have their sort of measurable and directable properties. And then the whole is just a big pile of those things bumping into each other. It's like a very dehumanizing view in some sense. It views the world through a lens through which the whole distinction between life and non-life is absent a priori. But then there's a shift in perspectives that's possible where you can look at that same thing. You can look at the same collection of matot and you can see a living whole. And it's a question of whether you have the ability to talk about the same part of the world in sort of two different languages. So in another basic sense, this clearly is about a transition from something that's not alive to something that's alive. Then when you go over to the tzaraat, the what is often mistranslated as leprosy that Moses experiences, the snowy anomaly in his skin. What's interesting about that, first of all, is in the Torah, tzaraat is clearly about the boundary between life and non-life. Aaron HaKohen elsewhere describes it as such, and also the mitzvot associated with the tahara of the Metzorah, when you're trying to do the purification of tzaraat, it's very similar to the tahara of the Met, like the association with death. You're using a lot of the same things in both of those mitzvot. So the Torah is telling us this is about the boundary between life and non-life in that way. It's also in Moshe's skin, which is the boundary of his body. So it is the boundary of a living thing that separates the living from the non-living surroundings. And what's striking is just the idea to bring in snow. It's such an evocative contemplation because snow, to the naked eye of an individual experiencing the world at any time in human history, is both itself an object whose boundary is very difficult to define, right? It's impossible to trace the boundary of the snowflake because it's so fractal and crenellated and it's not smooth. So it's all about the ambiguity of a boundary. And also snowflakes are themselves in their own way a more lifelike piece of the world than some parts of the world. They're not alive, clearly, and it is straining things perhaps to call them lifelike, but what I mean by that is that they are not straightforward in the way that an ice cube is. An ice cube is just a crystal where everything is very regular and neat and you can see through it because it has all this regular order. The snowflake has order, but it also has this kind of branched behavior that starts to look nearly random. And it comes from the fact that snowflakes actually emerge at a more complex boundary between different kinds of environments where there's some hot air and some cold air and some moisture, as opposed to just like slowly cooling down water in a jar so that it freezes solid. So it's also about this kind of, it's a little more of a technical point, but a non-equilibrium kind of thing where you have flow of energy from hot to cold while also mixing together with matter. So it starts to sound kind of like an energy source that can lead to organization that's more lifelike. And indeed, this isn't even an idea that has escaped other ancient traditions when they're trying to contemplate what life is like. Frost is something that comes up now and then. So I think it is kind of speaking to a relatively universal aspect of the human encounter with the complexity of life and searching for talismans in the natural world that remind one of that. So lastly, the third oath, the third sign that's given to Moshe is that he should take the water of the Or, which is the Nile, and pour it on the dry ground, and it will become dam bayabeshet, blood on the dry ground. And interestingly, it's quite specifically not just water mixed with dirt that's getting you blood. I mean, this is already, in a sense, the easiest one to say this is about the boundary between life and non-life, because it's all about the dust of the earth on the one hand, which is what we're told by the Torah we're made of, and blood, which is clearly, the nefesh, the holistic body connecting essence of life, as described elsewhere in the Torah and in the laws of Korbanot. So going from mud to blood is clearly the boundary between life and non-life. But it's not just water plus dirt makes mud, it's river water. And that's so important, again, analogically to thinking in terms that physicists think in, because river water, what's significant about it is that there's flow. There's flow of matter and there's flow of energy. So it's not enough just to mix things together and put them in a pot and see what happens. It's about things flowing in and things flowing out, and not just matter flowing in and out, but also energy that can activate motion. And when you put those things together, when you have flowing water and sediment, you get these incredibly complex branch structures. This is an aerial view of some kind of water network emerging from underground pools, I think in Western Africa. And you can see, I think I was in a parking lot in Newton once, and I saw something like this just because some water and mud had rolled down a hillside. And you see these complex branch structures emerge very easily under the right conditions. And so again, we're not saying that's alive, but what we are saying is there's something that's immediately in intuition, or in intuitive terms, evokes to us the more lifelike in the material world when we see flow of matter and motion in combination with some working material like mud or sediment that can be combined in different ways to form structures of different shapes. So that is just saying, okay, maybe there is a passage in the Torah that is taking up this topic. But I think the thing you have to ask now is why? Why would you bring up this topic? What does the Torah have to say? Because I don't think it's trying to be a science textbook. If it brings up a topic, it's because it has a commentary for us that's relevant to the task of being Ovdei Hashem, of serving Hashem, and learning about how to do that by studying the Torah and its commentaries on the world that we live in. So I want to open things to discussion, and hopefully we can cover that last aspect, but I try to get into that at the end of the book as well. And I do think there is an aspect to the commentary that points in that direction. But this is starting to give you a sort of aerial view of everything that you find there. There's a deep dive into some of the concepts in the physics, and an attempt to use these talismans that are provided from Sefer Shmot, from the book of Exodus, as sort of pedagogical tools for making that physics more tangible, more connected with what you would call kind of the everyday experience of the human being. And in addition, trying to synthesize those into some discussion at the end of, so what does the Torah want us to make of the possibility of viewing life as a phenomenon of materials? And how should we react to that if we're concerned about moral implications and other dimensions that don't really arise when you talk about the world in the language of physics. So with that, I'll just provide you with this information in case people are curious, but I'd be very happy to discuss and carry things forward from here in a more interactive way.
Here, Jerry, why don't you, yeah, okay, I was gonna say, all right, we don't have such a big group. Anyone have a question or comment? You can unmute yourself.
So, very fascinating, Yasher Koach. You were talking about random particles and formations of random particles that turn into life, or rearranging from life to non-life. To me, that suggests entropy in some way. So would you say that life would be the minimization of entropy, or is it some kind of maximization of entropy that's somehow stable?
So that's a great question. Definitely that entropy is a topic that often comes up in this discussion. And there's sort of I have a formal theoretical physicist's dodge for the topic of entropy, because I think that it too quickly turns into a qualitative way of talking about the world that can become a little bit unrigorous and intuitive, and then ends up being misleading, specifically when we talk about systems like this. So entropy is a term from physics, which was originally discovered in the era in the 19th century of studying heat flow and heat engines and all sorts of things that are very macroscopic. But what it starts to become eventually, as physics matures towards the end of the 19th century and into the 20th century, is it's about counting the number of ways that you can arrange a collection of particles so that they all have the same property. So for example, if I want to talk about taking the air of the room that I'm in and collecting all the molecules into the corner of the room so that there's a vacuum in most of the room and then just all the air molecules are in the corner, there are far fewer ways of doing that than there are of spreading the air molecules over the whole room. And so what we would say in the language of physics is that it's a much higher entropy arrangement to spread the air molecules all over the room, because there are lots of ways of doing that, whereas there are far fewer ways of just collecting them all in one corner. And we sometimes use an example like that to give intuition for the second law of thermodynamics, which states, but with more kind of asterisks and things that make the statement rigorous, that the entropy of the universe is supposed to be increasing. And so if entropy is increasing, it's hard to express what that means when you talk about something as big as the universe, but the basic idea is that we think of things as tending towards higher entropy, and that often is a good predictive principle. Like, I'm not worried that the air is going to collect in the corner of the room right now, because it's just so unlikely that it would do that, because the entropy of spreading out over the rest of the room is so much greater. But I think what that example points to is that it actually depends on the scenario. I could bring a vacuum pump into the room, and using work energy, I could pump the air into the corner of the room, and then I could make a vacuum, right? And so sometimes you can create low entropy things in the world as long as you're willing to expend enough energy and exhaust heat into the surroundings while you're doing that. So in the end, it seems like what we really care about, and this is how I tend to talk about the physics when you go a layer deeper with this stuff, is instead of talking about entropy, let's talk about probability. Let's talk about making a theory for the likelihood of something happening. And then what you find is low entropy things are less likely, all things being equal, because they are low entropy, but sometimes they're still the most likely thing because of the other factors that weigh in. Entropy maximization is not the only thing that impacts probability. And so life-like self-organization kind of comes to the fore in settings where it turns out you can lower the entropy of things in your system as long as energy is flowing in the right way. And then the real factors that matter to probability are some other terms in the equation that sort of overwhelm the pull of increasing entropy.
So Jeremy, I'd like to build on that last answer. I believe you used the word, first of all, this was brilliant and challenging as always you are. Thank you. And so you mentioned, I believe, evolution in sort of a generic term. In your, does any of what you're teaching today have any implications for the possibility of this having all been random without guidance, as evolution usually implies? Or did this give more credence for the idea that there has to be some arrangement for these very improbable changes to occur?
Yeah, I think it's certainly a very pertinent question in this kind of discussion. So I think the way there are two aspects to that. So on the one hand, I think that sometimes when we think about either evolution or other aspects of what we think about as the origins of life, part of what sometimes comes in the discussion is attempts to argue for the probability or improbability of certain events taking place. And what's true is that whenever you come up with a theoretical model that improves your ability to speak with precision about how to estimate the probability of things happening a certain way given certain assumptions, then sometimes what that allows you to do is to take arguments that had been made previously saying such and such is very unlikely, and you can point out, oh no, actually this aspect of things, which you thought was unlikely, was really much more likely than you thought. So for example, I think sometimes when people talk about the origins of life, they imagine this very naive scenario where before you have life in the sort of primordial soup that we're imagining, before you have the forces of natural selection and Darwinian evolution and whatever getting rolling and kind of making it possible for beneficial traits to accumulate and all of that, that you just kind of have this random mess that has no particular specialness to it and how it's put together. And I think that what is true is that this kind of a modeling framework allows you to think a little bit more precisely about, according to physical theories, if we want to make those assumptions, then what kind of special structures can we get from matter that look in some ways quite lifelike to us, that you actually don't need Darwinian evolution and selection in order to produce. And so like this sort of toy example of a thing that looks like a motor that you can just kind of get for free from the fact that energy is flowing into a system at a particular frequency and things can randomly jumble around and assemble.
Your answer is breaking up.
Oh, sorry. Can you hear me now?
I can hear you fine, Jeremy.
Great. Okay, so the fact that you can get something that looks like a motor from what seems kind of like a naive and random initial condition, that's showing you that with primitive assumptions in a model of things that are random, there are some things that maybe seemed very special and non-random previously. So I think in one way, a theory like this chips away at certain particular arguments people might sometimes make for this is very unlikely to happen without some kind of stacking of the deck. Because what we then see is, oh, here are examples where we see something that even though it was quite random in how all the initial conditions were defined and everything, you still get something very seemingly special looking at the end. I think that being said, what always is true in discussions about, let's say, the origins of life and whether they're random or non-random and all of that, is that people need to admit to themselves which modeling assumptions they're making in that discussion. Because physics, for example, can never prove to you that anything about the universe and the way that it works is random. What it can do is it can assume certain things are governed by very ideal randomness. And then it can, on the basis of those assumptions, show you how making those assumptions helps you to make certain predictions. So ideal randomness, you have to think of as being like the perfectly straight line or the perfect circle. It's a mathematical idealization. It's a contrivance of human beings to help define the mathematical structure of a model. And then what you could say is, oh, look, I made a model, and using the idea of ideal randomness in this model, I can predict or explain this thing that I observe. But for you to come to observations in the world and say, I'm going to prove to you using my analysis of these observations that such and such is totally random, that you can never do, because there always is an alternative hypothesis of subtler non-randomness that can't actually be distinguished. Sorry, just 1 second. I think one of my kids is banging on the door. All right, I think he ran away. Good. So I'll get to him in a few minutes.
As an example of randomness.
Yes, yeah, exactly. So so I think that with regard to zooming out on the whole question of the beginning of life and whether it's random or non-random, I think that what you always have to admit to yourself is that you're going to be the one devising a model of the likelihood of the universe being the way that it was in its original construction. And whether that is likely or unlikely has to do with the modeling choices that you make. So I don't think that science ultimately proves to us how to look about that, how to look at that. I think we have to recognize our own role as the model constructors in that discussion.
Jeremy, I can ask you a question that will sort of, I think, maybe segue to your conclusion if you're able to, if it's okay. So again, first of all, thank you very much. And like Rob said, it's always challenging, enlightening, a lot to think about. What you seem to be saying is that pointing out that sort of the boundary between things that are alive and not alive, it's a little bit more fuzzy, or there's certain characteristics of things that are alive that you find in things that are not alive. Just stuff you're showing us, can absorb energy and react and organize itself. And it's like some stuff is partially alive, and then there's other things that are 100% alive. So I'm not sure what you've obviously thought about this a lot. What morally, what ideas, what lessons, life lessons do you take from that in terms of how we see the world, how we, whether it's how we see what we call things that are not alive or how we see things that are alive? What do we take from all of this?
So this is something where it becomes the topic of the last chapter in the book. And I think it's something that's kind of hard to deal with very well standing on one leg. So I can only kind of hint at where that discussion leads. But I think it's in a sense the most important question in terms of how to react to this all this thinking, because is the point that if you look at living things through the lens of physics, they don't seem like they're less material phenomena, and that therefore they're not special, and that therefore they don't matter in any sense? That's really not the point that I'm trying to make. But I think if you're going to make a different point, then it is about how do you read things from the perspective of the Torah, with the commentary that it's making, by involving this discussion with the passage that it's bringing in, the ideas that it's bringing in. And I think that the point ultimately is going to be that if you are going to see other kinds of meaning in the phenomena of the world that are not sort of devoid of moral meaning and purely physical, then that requires a brit, or a sort of a commitment to talking about the world in a terminology that introduces those concepts. And I think that's why actually the concept of tzara'at, and also the image of blood on the dry ground, which recalls Cain and Hevel and the first murder, those are not accidental aspects to this passage, because it's pointing out the state murder just material, blood on the dry ground, like that we shouldn't care about more than mud on the ground? Or does it cry out, as Akadosh Baruch Hu says to Cain, does it have an agency or a status that matters? And similarly with tzara'at, is tzara'at a physical phenomenon, or is it a phenomenon in halakha that we define that takes the physical world and turns it into something that can have a new kind of meaning? So I apologize that I can't go much over time to try to elaborate on that aspect of the discussion, because I think it's a very interesting one, and I can only say it's a good teaser for the last chapter of the book if people are curious. I think I probably need to run, but this has been a great pleasure, and I appreciate very much the opportunity.
Thank you very much, Jeremy. Thank you, Mordechai and Sharon and the Kramers for sponsoring again, and it's good to see everyone. I hope everyone is doing well. Have a good night, everyone.
Thanks, everyone. Have a good night.